Hello and welcome to the video on chapter number 4 of collective choice and social welfare. In this chapter, we will be dealing with social decision functions, where we'll essentially try to resolve what we proved in the last chapter in terms of Arrow's impossibility theorem. And the next step when we get a theorem whose result we don't like is to try and weaken the conditions and see if the result changes. And indeed, as it turns out, it does, though with a few caveats. So in this chapter, we will relax condition O. Right? Condition O, if you remember, was that the collective choice rule must yield a social welfare function, i.e. an ordering. So it's complete, flexible, and transitive. Okay. This was condition O, and of course we proved that with the other four conditions, these conditions were incompatible, and we proved Arrow's impossibility theorem. Right? So here we are going to weaken this condition. We call it condition O star, which is the collective choice rule must yield a social decision function, or an SDF. Right? Now, what is an SDF? We have to define an SDF. So, define an SDF is a collective choice rule which gives an R such that for all S subset of X, C of S comma R is non-negative. It's essentially, if I give you any subset of the set of social states, there should be at least one best element. So this is called a social decision function, because essentially you're being able to decide from every set which is the best element, right, or the choice element, whatever. So this is a social decision function, right? Now, for finite X, right, social welfare function implies social decision function. Why is it so? Because an ordering, right, over a finite set X means that the collective choice, the choice function over the subsets is always going to give you a result, right? We proved this in the first chapter, right? But not the other way around. So what this means is that there are SDFs which are not SWFs, but as every SWF is an SDF, right? So we have essentially broadened the sort of collective choice rules which we can use. For infinite X, no such relation exists. So I'm trying to show you how an SDF is a V. In the case of finite X, an SWF is an SDF is clearly weaker than SWF because it is a larger set of collective choice rules. For an infinite X, there's no such relation, so it's a completely different condition rather than being a weaker condition, right? So this essentially gives us a result which we have been waiting for, which is why we did this weakening, which is lemma. Okay, this is a theorem. I'll use the terminology the book uses so that it's easier to follow. Theorem 4.1. There is an SDF satisfying the other conditions of Arrow's impossibility theorem, right? It was U, P, I, and D. Right? Proof. How do you prove this? Well, we have to use an example here. This is for a finite set. For an infinite set, there's a different result. Okay, So how do we prove this? Well, define x, p, y if and only if for all I, x, r, I, y is true, and there exists I such that x, p, I. This is how you define x, p, y, and you define x, r, y if and only if y, p, x is not true. This is the definition. This is my collective choice rule. This satisfies all conditions. Okay. How do we show this? Right. So what are the conditions it has to satisfy? Let's see one by one. Condition P, I, and D. Very obvious proofs. I will not be including this, nor does the book. Right? To show that R as defined above satisfies these conditions. It's not a problem. So now we have to show U and O star is satisfied by this. Okay. Now let's see. In the first chapter, we proved that for a finite set X, right, a choice function is well defined when using a binary relation, if and only if the binary relation is complete, reflexive, and acyclic. This was a very important result which we found. Another sufficient condition, though not necessary, was that the binary relation would have to be complete, transitive, and quasi-transitive. As it turns out, the R that we have defined here is quasi-transitive. And this is very easy to prove. Right? So let's say x, p, y, y, p, z. So you see then, for all I, x, r, I, y is true, and y, r, I, z is true. And there exists j such that x, p, j, y, and there exists k such that y, p, k, z. Now this very clearly implies that for all I, x, r, I, z is true. Now, there is this k such that y, p, k, z is true. Right? But for all I, x, r, I, y is true. So that includes k. So x, r, k, y and y, p, k, z implies x, p, k, z because the individual orderings are orbitals. Right? And there exists I such that x, p, I. So we are done. So x, p, z. Therefore, R is quasi-transitive. But this means that for any domain, right, the choice function is defined over this finite set X, something which we proved in the first chapter. For every quasi-transitive binary relation, which is complete and reflexive, this is true. Right? And completeness and reflexivity can also be checked very easily for this binary relation. Again, I will be explaining that. What is important, right? Now the question is, so we have proved that an SDF exists. Why does R, as defined here, not satisfy Arrow's impossibility theorem? Right? The answer is, it is not transitive. So it is not, so this collective choice rule has not yielded a social welfare function. Right? And the counter example has been given in the books. I will not be including it here. Right? Now, as it turns out, we can actually strengthen this theorem further. So we define a few new conditions which we will impose. And in fact, we'll actually strengthen certain conditions. Let's see. So we will define two new conditions. Right? This means for all I, x, r, I, y, and there exists x, p, I, y. Right? If this is true, then we have x, p, y. This is stronger than P, if you see. Okay. Any social welfare function which satisfies P has to satisfy this as well. You can check that very easy. Condition D star, which is that for no individual is there a pair XY over which he is decisive, over which he is a dictator. So D is also stronger than D. D star is also stronger than D. How? Because D rules out any global dictator. It says that there cannot be an individual who is decisive over every pair. Here we say there is no individual who is decisive even over a single pair. Right? So this rules out local dictatorship as well. Which gives us our next theorem, which is theorem 4.2, which is that there exists an SDF satisfying U, P star, I, and D star for any finite set. Right? Proof, same collective choice rule to be used. All right, the same collective choice rule which we used in the previous proof, right? Satisfies P star and D star as well. Once again, very easy to check. Very easy to check. In fact, if you prove that the R we defined earlier satisfies D, a very similar proof will work for D star as well. All right, and P star actually comes immediately from the definition, so I'm not going to include that either. So we will move on now and deal with infinite sets. Right. Now comes theorem 4 star 3. There does not exist any SDF satisfying satisfying U and P. Yeah, this is actually a very strong theorem for infinite X, for an infinite set X. So this is a troubling result at first, right? Because it tells you that what holds for finite sets doesn't hold, and in the impossibility theorem is essentially extended to infinite sets as well. And this is the proof of this is again very simple. We will have this for all j, suppose xj plus 1 p x, right? And we can hold this holds for all j and all I. Yeah. Okay. And this sort of individual ordering is admissible under U condition U, which is an unrestricted domain condition, as we have done for all counter examples before this. Right. So check. Right? There is no socially best element. Therefore, there is no socially best element in X. Why? Because if you choose any element, say xk, then xk plus 1 pxk, right? So xk cannot be the best element. But this holds for all k because it's an infinite set, so you can't run out of elements, right? Now, the understanding here, however, is why is this true? Why is this theorem true? This theorem is true because over an infinite set, even individuals who have fully ordered preferences may not have choice functions, individual choice functions, right? So in a paradigm where individuals within society are not being able to have a choice function, well-defined choice function, it is unreasonable to expect that society will have a choice function, right? So if we impose certain conditions on this situation, then we see that this theorem gets resolved as well, just like the previous ones. So let's see what the next theorem says. This is theorem 4 star 4. If at least one Ri exists which generates a choice function. Did I misspell generates? Yeah, embarrassing. Anyway, generates a choice function. Then there exists an SDF satisfying P, I, and D star and U, except above condition. What does this mean? So first of all, 2 things to note. First of all, it does not satisfy P star, but D star is satisfied. So we still have the original Arrowian conditions. And U is satisfied, excluding this above condition, which is that there should be at least one Ri which generates a choice function, which is reasonable in this regard because of the reason I told you earlier. Right? Proof, very simple. XRY, if and only if, for all I, X, Y, PIX is not true, then XRY should be true. Right? Here, if X belongs to this, right, the choice function over a subset S using an individual ordering I, then it also belongs to this. Because then XRIY is true and therefore XRY must be true. Very simple, because if XRIY is true, then YPIX cannot be true. Now, that's very simple. And this is it. Right? You can show it satisfies PID star very simply. Again, I will be excluding that here. Okay? So it seems prima facie that we have resolved the Arrowian problem. We weakened one condition, O, rho star, and suddenly for finite and infinite sets, we face no problem. Okay? But there is a problem. The problem is that any binary relation which satisfies the choice function being defined can still yield problematic properties. Right? And let me take you back to the first chapter here. In the first chapter, we looked at properties alpha and beta, right? Which were certain rationality conditions. Right? And we saw that even if a binary choice, even if a binary relation creates a well-defined choice function with a set X, it may not satisfy beta, even though it satisfies alpha, right? And you can check up very quickly the definition of property alpha and property beta from the first chapter of the book and sort of rejig your memory. It's on page 63. Right? So the problem here is that an SDF will not satisfy property beta. So even if we have resolved those Arrowian conditions, property beta is not going to be satisfied. Of course, Arrow didn't include property beta because it was not necessary, but property beta can be a reasonable condition. Right? Now, why is this? Let's look at an example of the sort of problematic social collective choice rules which we might have. So let's say that X, Y, and Z are 3 social states. X, P, Y is true. Y, T, Z is true, but X, I, Z. Now this sort of thing can occur for an SDF because PP transitivity is not true, right? So now let's look at the problem. You see, choice functions are still defined. So if you look at the choice function over the set this using R, we get the whole set. But if you have the choice function over this larger set, then you get only x. Why is this problematic? For very obvious reasons. It tells you here that essentially x should be equal to z. But now when you've included y, suddenly things become different, right? This is actually what property beta is all about, right? This is property beta being violated. Property beta being violated. Why? I don't know what's happened to my spellings today. Anyway, right? So this tells you that example, let's say the Beatles and Fleetwood Mac, right, are the best British bands. Right? But even though, but Beatles, the Beatles are also the best, let's say, global band, right? And Fleetwood Mac is not. You see the problem here. This was what property beta was all about, right? So property beta will be violated by an SDF, but not an SWF. Why? That's because of a result we proved earlier. Let me take you back to that result and write it down here. Lemma from chapter 1. If R generates a choice function, that is if CSR is non-empty for every S subset of X, if R generates a choice function, R is an ordering. If R generates a choice function and satisfies beta, then R must be an ordering. Right? And vice versa. We proved this in chapter 1. Right? So we get a theorem from this, which is theorem 4.5, right? Which again takes us back to square one. So you see, if I want R, my social choice binary relation, to satisfy beta and therefore not yield that sort of problematic Fleetwood Mac Beatles preference, then I need it to be an ordering. But that means I need it to be an SWF, right? So theorem 4.5 is a restatement of Arrow's impossibility theorem and this lemma. There does not exist any SDF satisfying U, P, I, and D, which satisfies property beta also, because the moment it satisfies property beta, it becomes an ordering and hence an SWF, right? And we know already that an SWF cannot satisfy these properties, which is Arrow's impossibility theorem. So in a way, we are again back to square one, although we have shown that a weakening of certain conditions gives us social decision functions which satisfy the Arrowian conditions, right? Thank you very much. See you in the next video.